Hello. So thank you very much to the organizers. It's been a great conference, and this conference has become a highlight of my year over the last few years. So it's a real pleasure to come here and talk about a result that we're really excited about. So I'm going to talk about the simulation of a topological phase transition in a fully frustrated two-dimensional lattice. And this is a result of a lot of interdisciplinary teamwork at D-Wave, starting with the design of the processor, moving up through fabrication and processor development, through quantum annealing experiments, simulation, and this all started with theory. So everybody in this work is or was at D-Wave, and Juan Carrasquilla, who is over here. He's now at the Vector Institute, but he was at D-Wave when we started working on this, and he said, "Oh, you guys should start looking at 2D frustrated lattices and see what things look like in the transverse field Ising model." So that's how this all started. Historically, the D-Wave processor, at least from my perspective, being a computer scientist by background, has been thought of as a discrete optimization oracle. This is kind of idealistic, but you can also think about getting a set of samples for some Ising problem, and you can look at this in terms of either a classical Boltzmann distribution or a quantum Boltzmann distribution. And Richard Harris last year talked about a result where he did a quantum simulation of a three-dimensional lattice, and he looked at spin glass to paramagnet phase transition and spin glass to ordered phase transition. So that work was kind of ideally lying in the zero temperature limit, and we know that we have a finite temperature, and for this work we kind of embrace that finite temperature and look at a phase transition that relies on competition between thermal fluctuations and quantum fluctuations coming from the transverse field. This, I think, is a really nice, clean demonstration of the kind of things that you can do with reverse anneal. And I'd like to emphasize that all of the experiments that we did for this project have no fitting parameters. So what you see is what you get. They have no post-processing, and they were all done through SAPI. So there's no kind of funny tricks going on. So in principle, you could repeat this experiment on the D-Wave 2000Q product. The KT phase transition, or the BKT phase transition, or just a topological phase transition is kind of a hot topic these days because it was a subject of the 2016 Nobel Prize given to Kosterlitz, Thouless, and Haldane for work on topological phase transitions and topological phases of matter, which were also studied by Berezinski, who passed away, I believe, in 1980. This is kind of an exercise in graduate level physics in the XY model. So we'll start there, and I'll kind of explain how this phase transition arises, and then I'll explain how you can get it in the transverse field Ising model, which is a bit counterintuitive because it relies on a winding of an angular degree of freedom, but the Ising model has up-down symmetry, so there's no angle there, or there's no direction at least. So in the 2DXY model, you have a set of spins which are represented by angles in the plane, and the XY Hamiltonian gives the energy of the system. Oh. Thanks, Eric. So the Hamiltonian is given by just a coupling strength, the XY coupling strength, and then you get the sum of the cosine between the angles of neighboring spins. So in this case, I'm just looking at a square lattice, but it doesn't really matter what it is. And you can see that the ground state of this Hamiltonian is just going to be a state where all of the angles are the same. And you can also see that, so there's no frustration here. All of the local interactions are optimal. You can also see that you have rotational symmetry, so you don't just have one ground state. You can rotate this ground state continuously, and we call this O2 or U1 symmetry. And so one of the interesting things about how this arises in the transverse field Ising model is that the effective XY model that we use to understand this system is actually discretized, and yet you still have continuous rotational symmetry above some other topological phase transition. So you have two topological phase transitions here. We're only going to talk about one of them because the other one is, I think, probably around 3 millikelvin, and that's just pushing things a little too far right now. So the key to understanding this phase transition is the appearance and interaction and energetic favorability of vortices and anti-vortices. So these are just kind of like vanishing points of a vector field, basically. And a vortex is what you get when you walk around a point in a clockwise direction, and then your angular degree of freedom also winds around in a complete rotation in a clockwise direction. An anti-vortex is the same but different. So you walk around in a clockwise direction and your angular degree of freedom rotates the other way in a full circle or winding. And these vortices and anti-vortices like to be in pairs, not just because of topology. So we know that by Stokes' theorem, if you have the appropriate periodic boundary conditions, for example on a torus, then you have the same number of vortices and anti-vortices. But they also like to be next to each other at low temperature, because if you walk around both of them, then you have less of an excitation. So if you walk around both of them, you get neither a vortex nor an anti-vortex in a certain sense in terms of a net winding, because the angular degree of freedom rocks back and forth but never winds in a complete rotation. Okay, so below the critical temperature, which is just given by JXY times pi over 2 in a very elegant derivation. Below this phase transition, the free energy prefers these vortices and anti-vortices to be tightly bound, which means that you don't want an isolated vortex, basically. And above the critical temperature, an isolated vortex or isolated anti-vortex is actually favored by the free energy, in spite of the fact that it has an excitation that diverges with the size of the vortex, basically. Okay, so above this critical temperature, you have exponential decay of correlations, and below this phase transition, you have power law decay of correlations. In other words, quasi-long range order. So this is what we're going to see in the D-wave processor. And this was discovered in the early 70s, and then since then has been observed in many physical systems. So starting in the 70s, it was observed and is kind of typified by the superfluid helium transition in thin films and thin films of superconductors. And more recently, it's been observed in two-dimensional Bose-Einstein quasi-condensates and graphene-tin hybrid Josephson junction arrays. So those sound pretty interesting. But it's also been theorized and simulated in QMC in the triangular AFM transverse field Ising model. And this was actually, this comes from the stacked magnet in work that was done in the mid-'80s. So this is kind of the typical frustrated 2D lattice. You have AFM couplings in all these triangles, and all of the spins want to be different, but because there are 3 of them, they can't all be different, and so you have frustration. And so let me just explain how you get a mapping from these triangles to a rotational, an angular degree of freedom, and that's where the vortices and anti-vortices can be seen. So we take the typical Hamiltonian of the transverse field Ising model. We don't have any fields, so we just look at the couplers, and they're all the same. They're all +1 AFM. And then you have a perturbative transverse field. So we're just looking at the low energy description in the perturbative limit. And in the classical system, you have 6 out of the 8 states are ground states. You only have an excitation if all the spins are the same. And you can see that you have two ground states here with energy minus J, and they differ by a flipping of this bit, or a spin. And so it doesn't really matter which value that takes if the other two spins are fixed. And so if you put on a perturbative transverse field, this spin falls into superposition, or it aligns with the transverse field, and you get an energetic contribution of minus gamma. So this is your transverse field. And so the order in the system, order from disorder, comes from the fact that you want to maximize the number of these transverse field aligned spins. Okay, and it's disorder because you're adding quantum fluctuations, yet somehow increasing the order of the system. And then you can just look at this and you can say, well, in the first order perturbation, I still have six-fold ground state degeneracy. I just have a red, white, and a blue spin, and I can permute these in 6 ways. And these 6 permutations will map to 6 angles. So they map to 6 angles like this. I'm not going to explain exactly how to do it, but it's not complicated. And you also get another 6 angles coming from the classical ground states of an AFM triangle. And you also have the 2 excited states of the AFM triangle, up, 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 and down, down, down. And this is where the pseudospin vanishes. So just like a vortex or an anti-vortex, you're going to have a vanishing point of this angular degree of freedom. So we want to look at an order parameter. We want to see that we're getting the right statistics out of this system. And so we're going to derive an order parameter just by taking the pseudospin across the whole system and taking the average of it. And that gives us a complex number. So you can see this is a perturbative ground state of a portion of the lattice. So you're actually just tiling this perturbative ground state across the lattice, and you get the same pseudospin direction everywhere. And so if you take the average of this over all the plaquettes in the lattice, all the triangles, then you just get this order parameter. And if you want to turn that into a real order parameter, you just take the magnitude of it. So you're just taking the average pseudospin over the lattice, and then you're taking the magnitude of it to get a real order parameter m. And we can also look at psi, because we expect this to have continuous rotational symmetry due to renormalization above a certain temperature. Okay, so what happens if I make a little fluctuation in this pseudospin field? Well, you'll notice that everything is okay over here, everything is okay over here. We've just kind of picked a different perturbative ground state to tile. But here you have 2 triangles that have no floppy qubit, no energetic contribution from the transverse field. And this means that you get a small excitation in the perturbative picture. And this excitation is linearly proportional to the transverse field. And so what happens is you actually get a 6-state discretized XY model that's your effective model that has a critical temperature. It has a coupling constant and therefore a critical temperature that is linear in the transverse field. Okay, so what does your phase diagram look like? You have temperature divided by J. This is just a normalization constant called 1 if you want to do QMC or something. So you have your temperature and you have your transverse field, and because the coupling strength of the XY model, the effective XY model, is linear in the transverse field, so is the temperature, the KT critical temperature. And so you just get this perturbative argument, which is a line, and then as you increase the quantum fluctuations in the system, you actually get this critical temperature dropping down until finally you get to a quantum phase transition at some critical transverse field. And notice that I told you we have 2 phase transitions, but we're only really going to look at one of them. This is because we have a discrete effective XY model, not a continuous XY model. So here you have a phase transition where you go from quasi-long range order to long range order as you decrease the temperature. But again, this is at like 3 millikelvin, so we can't look at this. So in the ordered phase, you get this concentration of the order parameter around these 6 clock states. And in the critical KT phase, you get U1 symmetry. And in the paramagnetic phase, you get a small order parameter, although we're only looking at finite-sized lattices, so it will be finite. And this phase diagram was mapped out by Mosner and Sondy in 2001 through theoretical arguments coming from the stacked magnet, and by Isakov and Mosner in 2003 using quantum Monte Carlo. So we've taken this system that has been studied. So it's a system of interest that's been studied using QMC, and we're going to study a similar system using the D-Wave processor. Okay, so this is nice. We have a two-dimensional lattice, and we have a quasi-two-dimensional chip. So it feels like we're in our wheelhouse, kind of. And we have 16 unit cells across here, so we're going to have a lattice width of L equal 15. You throw away some stuff on the sides. But we don't have triangles. We all know that Chimera doesn't have triangles. It's a bipartite graph. So we're actually going to look at a lattice that has the same heuristic low energy description, but has microscopic differences. So, and therefore has quantitative differences in the phase diagram, but it's qualitatively the same phase diagram. So we are going to couple together FM chains of 4 qubits with couplers of strength minus 1.8. And then just like in the triangular lattice, we're going to put the remaining couplers at +1. So just like in the triangular lattice, we have a frustrated bond in each plaquette. And just like the triangular lattice, we can define the same angular degree of freedom and use all the same machinery that we used before. So this is what the hardware output looks like. So when you get a classical state out of the D-Wave processor, you end up being able to map it to pseudospins. So these are your plaquettes. These are squares and octagons. And so you just kind of, rather than looking at the spins, you're turning the spin state into a state of pseudospins. And then you're looking at the vortices and anti-vortices and topological features in this effective model, which I think is pretty neat. So here you can see that there's a vortex because you walk around it in a circle, and the pseudospin walks around in a circle as well. And here you have an anti-vortex where it goes around the opposite direction. And due to technical reasons, the vortices appear on octagons and the squares appear, the anti-vortices appear on squares. Okay, so you can see the phase diagram of the square octagonal lattice. It looks kind of the same, except you have a gamma to the 4th power here instead of gamma in the perturbative regime. So you have a KT dome and an ordered dome, and we're going to look at the paramagnetic to KT phase transition. And you can actually visualize in this temperature transverse field plane, you can visualize the annealing schedule of the D-Wave processor. So if you fix your temperature, you just have, as parameterized by S, the annealing parameter, you have a transverse field divided by temperature and a coupling energy divided by temperature. And the important regime here is going to be between S equals 0.2 and S equals 0.3, so near the quantum critical point of a single qubit. So I mean, we're really used to solving classical problems with the D-Wave processor and just annealing in a straight line. So we're not going to do that. We're going to reverse anneal, and we're going to try to sample the statistics of a non-classical system. So rather than just annealing in a straight line, and by that I mean that the annealing parameter S is a linear function of time, we're going to do what a couple of people have already talked about, and I think there's a lot of really exciting work. Hopefully we're going to see a lot of it next year. You start at the end of the anneal, you load in a classical state to your processor, and then you want to just sit there and evolve the system of interest, so S equals 0.25, for example, and you're gonna go back to S equals 0.25 and pause for a really long time. Here it's shown as 16 microseconds, but we actually do 65 milliseconds, so very long time. This is a very sensitive system, so we have to be very slow and very quiet. And then once we're done relaxing, we get out as soon as we can without disturbing the statistics of the system that we've relaxed. And we do this over 1 microsecond in a quench. Okay, so we actually don't just do that once. We then take the state that we get and we put it in as input. And we do that again and again in a loop that very much resembles a Markov chain Monte Carlo approach, except your Markov step is a quantum evolution. So we call this quantum evolution Monte Carlo. Maybe QCMC would be better because we need to remember that it's a chain of updates. And so we just follow this cycle of input classical state, quantum evolution, and readout classical state, then go back to the beginning. And it's very common in MC-MC methods to start from two different points. This is the order parameter m. So we're starting from a random state and a very ordered state. And then we're going to estimate the statistics of the system by doing a bunch of reverse anneal protocols in a chain. We're going to do 50, and then we're going to throw away the first half of them and say, well, we were just kind of forgetting where we came from. We were burning in at that point. And so we're just going to look at the statistics from the last half of it. So in MC-MC methods, you would want to make sure that you're converging to the same place no matter where you start from. And indeed, this is what we see. If you start from a random state or an ordered state, it doesn't matter, you end up at the same place. So these are the results as a function of S for QMC and QA, the D-Wave processor. And you can see, as I mentioned before, there are no fitting parameters in this work. We've measured the temperature independently and measured the schedule independently. And so you can see that we have very good quantitative agreement with QMC equilibrium statistics. So even though QMC we know now, for example, based on the first 3 talks of Tuesday morning, that QMC cannot simulate the dynamics of quantum annealing, but it does get to the right equilibrium statistics, regardless of whether or not there's a sign problem. Sorry, if there is no sign problem, let's say. So we get very good agreement here between S equals 0.24 and S equals 0.3, but it's kind of not very good over here. And we're really overestimating the order. And the reason for this is that we're quenching. And at S equals 0.2, the dynamics are very fast. Our quench takes a microsecond, and so we just are not fast enough to get out before we kind of splash the system around during the quench, basically. So if we want to look at, rather than just looking at the expectation of the magnitude of the order parameter, we want to look at the complex order parameter itself. As I said, we would expect a U1 symmetry in the complex order parameter in spite of the discrete nature of the effective XY model. We can see that over here we get well, I'm not sure if you can see that, but we get a smearing of the order parameter. This is QA, this is the D-Wave processor, and this is QMC. You get a smearing of the order parameter that is consistent with evolution during the quench. But over here, near the peak of the order parameter, you get this nice tight ring that is very similar to what you see in QMC. So we're really happy about that. So this is the first piece of evidence. And then you would also, at least heuristically, you would like the peak of the order parameter in S to correspond to where you're cutting across the top of the phase transition. And indeed, it is close, but not exactly the same. But as I said, we're dealing with a lattice with a cylindrical boundary condition. So we don't have enough space on the processor to do a torus. But we're doing cylindrical boundary condition. But we see the same peak location in QMC and QA. So we know that this is a finite size effect that's exacerbated by the boundary condition. So the fact that we get very good quantitative agreement with QMC allows us to wash our hands of all these kind of fussy issues with the boundary condition, which is really nice, because otherwise it would be hard to explain. So the big smoking gun for a KT crossover going from the paramagnetic to the critical phase is the onset of power law correlation decay. So if you just look at some spin in your pseudospin, you just look at the whole lattice. Again, this is open boundary and periodic boundary. Now you're just going to be as far away from the open boundary as possible, and you're going to walk along in the periodic direction. You can see the correlations decay as you walk further and further away. And so with quasi-long range order, you would expect this to be a straight line in this log-log plot. And you're just looking at phase correlation here. And so the blue here, here and here is QMC data at 2 temperatures, 8.4 millikelvin and 21.4 millikelvin. And then this very closely matches the QA data that, again, we take at the same temperatures. And so we can estimate the universal critical exponent of the 2dxy universality class, which should be 0.25. It should be a quarter, and we estimate it as 0.37. But we estimate it as 0.37 in both QMC and QA, so we can, again, wash our hands of this issue and say it's a finite size effect that is exacerbated by the boundary condition. Another way to look at this onset of power law correlation decay is just to look at the order parameter as a function of the lattice width. So you look at different system sizes, and even though we would expect an overestimate, and indeed we see an overestimate when you look at small systems because they're evolving during the quench, we get really good agreement between QMC and QA, and you get what appears to be pretty good agreement with power law regression. And so you would expect this to have half the critical exponent of this, and it approximately does in both QMC and QA. So we're really happy to see this. Now, I'd like to just mention for a minute, we've only done crude measurements of how fast this is. So you want to look at the relaxation dynamics, and so what you do is you started in two classical ground states. You started in an ordered state and what we call a striped state. This is classically ground, but in the quantum system, it's a metastable state. And you basically see how long QA and QMC take to get within some tolerance of one another. So here we set this tolerance to be 0.3, which is quite large. But you can see that as a function of S, the scaling of the D-wave relaxation time is much more gentle than the QMC time. And so you can kind of, this is QMC sweeps versus QA microseconds. And so you should add another 3 orders of magnitude to this. So it's right here, by this measurement, it's roughly 1 million times faster than QMC. And so this is nice because you have to do QMC to get the statistics of this system unless you're going to use a quantum simulation. So it's nice to see this, and it's nice to see that the advantage grows as long-range correlations become more and more important. And this is also consistent with the stuff that Boris and Vadim were talking about on Tuesday, where you have a mini band of almost degenerate states. In this system, you have many, many almost degenerate states, especially in the perturbative regime, and so you would expect to get a big speed up over QMC. So just to wrap up, we've done a quantum simulation of a KT phase transition, and we've gotten really good quantitative agreement with QMC. And we totally rely on the new annealing features, so we absolutely have to do this reverse annealing protocol to get good statistics. And this is a simulation of the transverse field Ising model, not just a roundabout way of getting at a classical system. So with that, I'll stop. Thanks.
All right, thank you very much. We have time for a few questions. We'll start off.
So I'm curious how you determine the transition point between the paramagnetic and KT phase, because it is usually very difficult to determine the transition point in the classical simulation of the classical XY model, because finite size effects are very strong, and one should be very careful to use finite size scaling and so on.
So let me just find this slide. We did, the short answer is we did a very exhaustive Monte Carlo simulation, and we used some specialized methods to speed up QMC. You saw how slow it was. So
QMC is okay. How about data from the DOA machine?
So we're not able to trace out the phase diagram with the D-Wave machine because of all these boundary conditions. So there's no way that we can get an accurate estimate of the critical temperature on these cylinders. So again, the boundary condition of our lattice is open on both sides.
Then what are those error bars mean?
The error bars are statistical bootstrap error bars, and they also include the difference between the estimate from the lower initial state. Sorry, this laser is not working quite right. The estimate from the lower initial state and the upper initial state. So these error bars include this difference and statistical bootstrap. They're 95% confidence intervals.
All right, in case there's another question, I think we have time for one more. There in the front.
So, I mean, how critical is it, this sort of looping of, taking the state that you read out and using that to feed the algorithm again? I mean, in principle, could you just keep using a random initial state?
Yes, but then every time you don't get to a steady state, you have to go to the people in processor development and ask for another order of magnitude in your anneal time, and eventually they stop talking to you and to answering your emails. So you can see in this slide, what we're doing is we're doing a single pause, and you can see we don't really converge over these timescales. So I've got some other data here as well. So this is S equals 0.3 at 8.4 millikelvin, so this is basically as slow as it gets. And you can see that it takes a few iterations at 65 milliseconds before you really get close to the other initial condition.
All right, so I think